Okay, um, I want to start off this second half by giving you just a very top overview of some stuff that I'm doing with Natalia Kranzina, who's at Copenhagen Business School. We're looking at PSID data, American data, and asking how is female labor supply tied up with fertility and home ownership? And could that help explain some of the trends that we've found in home ownership? That's the kind of question. And I figured that's a topic that would be appropriate for this conference. Or this whole week. I thought, though, at the same time, it's forthcoming. It's not really research anymore. It's almost out there. So just to give you a very top overview of what's going on, here's labor force participation in the 70s, 80s, 90s, and 2000. That comes from the Census Bureau, and they're sort of averaged across, is for age and different periods of time. And then the stars show median age at first marriage. Here they are. And then the dots explain median first birth, and they're more or less on top of each other. And then here is, whoops, sorry. Here is the time of first housing purchase. And you can see that the marriage and the first kid are pretty closely timed. They're going back, they're being lagged as we move down, as we move into the end of the millennium. And so are housing purchases. Now, first home purchase. Now, if you go and ask, well, when do people get rid of their homes? It's almost the same time. So there are less people, at least up until the turn of millennium, there were less people buying houses. There's a decline in home ownership, and that's driven wholly or almost wholly by people buying homes, their first home, later in life. It isn't that they go into old age homes earlier, certainly not now, but even then, not true. It is that people lag. They don't buy houses straight away. And of course, it's coincident with these other two trends. If we go just a little bit further here, here is the calendar time years, and here's the age, median age of first child. This is coming from the PSID now, as opposed to the census. Here's the age of the second child through the years, and here is the age at first home ownership. Notice how close they are. It's almost as if you didn't want to do very much economics and you just wanted to talk, you would say you get married when you're having your first kid and you buy your house when you've decided how big your family is going to be. Okay, that is the 2-second, maybe 20-second kind of response to what is going on in this world. Okay, there's one more thing that's going on, and that is that age at first ownership, as we see, is just going up according to this. The diagram's been just a little bit squished, so it's not exactly the same. Look at the average house size, also going up. People are buying later, but bigger, okay? So that's the other thing that's going on in this setup. Well, what could be driving this? Well, one thing you could say, some people would say, well, maybe marriage, people are getting married later. It's like, hold on, that's a choice variable, guys. That is not something that you give as being a driving factor. And in fact, the argument might be that part of the reason why people get married is to help insure their kid, okay? So that in Europe, you got insurance anyway, but in America, not so much. So if you're married, there's a kind of joint ownership aspect that really kicks in. Not so much if you're not married. And so, or weren't married when the kid was born. So driving factors we think of as, well, when do people finish schooling? Because most people don't have kids until they finish schooling, Okay, and that's right through even to PhDs, and that's why, you know, you're looking at people, females with PhDs. They're the ones that have the least kids. Then the wage rate is something else that's going on. Technology driven. This is female wage rate, guys. Price of energy going down. Difference between the genders essentially being obliterated because types of work. There's no gender. There's no real gender reason for differentiating between those genders on that basis. Maybe because of experience, stuff like that. Separate question. And then here's a housing price index. It's sort of going all over the place, up and down, but it's giving us a kind of a sense of variation. And you might say, well, a housing price is endogenous to this because people are, after all, buying houses later. That's the demand side. So isn't that affecting supply side? And my answer there is maybe in this model, no. The argument that we're trying to justify here is that actually housing prices are basically part of construction costs. And so if we think about construction as opposed to just personal housing, well, then maybe prices don't vary that much just by demand. That assumption is being contradicted right now in the States because housing prices are just shooting up like crazy as people want to move out of crowded apartments into nice suburban houses where they're separate. But of course, you know, then the issue is, well, is that a short-term or a long-term thing? And at least from the 70s through the 2000s, there was no factors like that. So there's a sense in which picking the period, that's not the reason why we pick the period, but picking the period is sometimes a motivating reason as to why you want the panel to look the way it does, because you're asking what kind of factors would be influencing things? What can we take as what was called predetermined or exogenous as opposed to the things that we really want to model? And then over here, we have the T-bill rates, and you can see interest rate, well, home borrowing rate's going to be higher than that, but often by just a point or two. Because obviously, if it's mortgaged, well, then there's a sense in which the bank owns the house. You've basically got T-bill going up and then down. And here's a home ownership that's going on in this period. This is just the census again. See how it goes up and then down? Same sort of way, much smoother. The only reason why it's smooth is because we only got 3 dots, okay? That's the census. Those are census dots. And so it may well have the same kind of volatility. But the significant thing is that people are buying more homes when the interest rate, well, the home ownership rate is higher when the interest rate is higher. You know, people thought, so what's going on here? Well, of course, a whole lot of factors are influential in this. But one thing you should realize is the following. If you own your own home entirely by the time you say 65, and that was true of this generation, well, then you're not paying rent. And so one of the ways you save is actually by gradually putting it into accommodation which you own. It's a savings vehicle. And so then the question is, well, when do you save more? When the interest rate's going to be high or low? Well, obviously a high interest rate gives you more at the end of the day than a low interest rate. So there is a kind of question here as to whether in a dynamic programming problem, optimally solved for a given set of parameters, people would buy more or less or transfer to home ownership earlier or later for a high interest rate versus a low interest rate. We can solve that problem with parameters for the primitives, etc. But it's not an obvious call, okay? It doesn't go one way or the other. That's as a theory thing. So here we're developing this non-stationary dynamic model. You see these trends are big. You know, this is not a station, does not look like stationary distribution over time. So we're going to allow for this non-stationarity with these secular drivers related to wages, that is wages relative to, say, capital, okay, for any type of quality of labor. Second, educational attainment. So people are also getting more educated over this time. Interest rates are also going to affect what's going on, as do, we're assuming, we're just looking at housing prices being driven. You'd need, if you wanted to have housing prices being driven by supply side factors as well, you're looking at the equilibrium, then you'd have to model as I say, probably the construction industry. And then what we do is we estimate this stuff. And then we ask, well, what would happen if we lived in an economy that looked different from this? Here's a reason why, as economists, we're not really that good at predicting the future, and we maybe shouldn't try. We're always wrong. And the reason we're always wrong is because there are all these non-stationarities that we care about. We know they're important, and we don't really know how to deal with them. So rather than go ahead and say, let's just punt, can we just be a little bit more scientific about this? Take our model, we've estimated it, and then we ask, in this model situation, what if it was like this? What if it was like that? And present that to the policymakers as opposed to making this bold prediction. Let the guys that want to jump off the cliff with, they think, bungee cords or parachutes, do it with their own hooks. Don't do it yourself. Just that's, at least that's a view that I have, because I think that economists run the risk of losing credibility if we pretend we can say more than we really can, have confidence. And where do we get our confidence? Our confidence comes from the data that we've got and the assumptions that we're making about our model, and also the assumptions that go into doing inference. Those are the things that we have going for us. That's where we have our expertise. That's what we should use. That's where we should stop. So one wouldn't necessarily want to do simulations on a steady state economy. For example, we could have looked at different kind of states and then asked, how would it work out then? Doing the counterfactual might be a little bit hard because we'd have to solve for a non-steady state economy, and that might take work. Okay, but there's that possibility. For in what Natalia and I did, just looked at two steady state economies. We looked at the 1970 situation. We looked at the 1990 situation. We said, let's benchmark at the 1970s, ask what would happen there in a steady state economy if everything was just 1970 values, and I mean, these guys are all the same. And then we asked, what does that look like compared to a 1990 situation where all of these drivers are up at the 1990 values? Now, we didn't actually do it quite that way. We said, well, let's change one of them at a time. How would that affect things? It's a kind of a factor decomposition. The counterfactuals were saying, how much of what happened in 1990 could be explained by perhaps something that went on in 1970, something that went in 1990, and then ask, how do these different factors contribute to it? That was our exercise. Now, several other ways of doing it. I don't want to take a strong argument on that. Let's go to the model itself. Okay. We've got births in here. We've got participation. We didn't look at ours, but we looked at the distribution conditional on the participation and the characteristics of the person. What was the distribution of ours? So we're actually saying, when you go out, when you participate, you're going to get this draw from ours and go from there. And that's, maybe we could have looked at an Euler equation on that, but we didn't yet. Well, not in this paper. And then there's an issue of whether you continue to rent or not, or whether you buy your first home. There's a kind of question, well, what happens after you replace the first home? Well, for a lot of people, they don't replace. They keep their first home. There's more than, I'd say, 50%. This is a number coming off the top of my head. I think it's way more. And then the issue is, to what extent even people buying a new home, to what extent is really that just a transaction cost and a pain because you've got to do the moving expenses, but really you're basically replacing your equity in the old home with the equity in the new home. Not as big a deal as buying the first home. Okay, that's for the most people. So by purchasing a first home, by definition, is a once in a lifetime decision. Then you might replenish, but we're not going to worry about that replenishing thing. And once you've got a own home, you've only got 4 choices as opposed to having 8. So here we've got the utility for the household. Really, in this model, we've got the utility of the female. The male is an add-on, okay? So get used to it, guys. We're imagining that the female is making the main choices in this household. She's the one that lives in the house most of all, more than the male, at least in this era, in the United States. She's the one that bears a lot of the fertility costs because almost by default, she'll be the main carer if the male wimps out or tries to. And at least in many countries, maybe not in Western Europe, but certainly Middle and Eastern Europe, at least up until in this period, women worked, sure, but they also took care of the kids. That was just the way. There's a fair bit of, I'd say more than anecdotal evidence on that score. And so that's our argument for just sticking with women's utility, focusing on that. Now, it doesn't capture everything, obviously. So, for example, two things we're not capturing. Number one, we're not capturing the fact that being married or being, and we mean by being long-term partner, it's a local public good. People are sharing things all over the place, not just kids. And so that is an aspect that we're not capturing, at least here. And it's an obvious way to move forward on this thing. Second thing we're not capturing is because we're focusing on females, we're not focusing on single males who buy houses. And so we're missing on that part of the market as well. And so there are definitely deficiencies here in terms of gaps in what we're not modeling. We're being internally consistent, but we're ignoring some stuff, even on the preferences side. But that's essentially what we've got. We've got utility from consumption, from leisure, and also from housing. And then that's driven by underlying characteristics like education, age, stuff like that, as well, and number of kids you've already got in the family, as well as these idiosyncratic epsilon shocks that are in there. So we parameterize that in a fairly standard way. Notice that we got an exponential distribution here. That simplifies things later on, because with an exponential constant absolute risk aversion, wealth plays a very limited role. And in the PSID, we don't have very good measures of wealth. And so you have the choice of ignoring it, or assuming that it is something, or putting a distribution on it, or taking a utility function where the wealth drops out in the theory, in theory, because the kinds of decisions that a poor person makes are the same as the kind of a rich person makes with respect to risk in the exponential utility model. And hence you're integrating it out that way. Got PSID, you've got to integrate it out one way or the other. Neither is satisfactory, because my house looks nothing like Bill Gates's house, seriously, let alone his yachts, and probably the same as you, otherwise you wouldn't be sitting in this room. And so clearly wealth does play a big role, and that's something that we're also not capturing. Having said that, we just march on, acknowledge it, and think, well, maybe that's a way. What can we get out of this model, even if we don't assume that? Okay, even if we're making this assumption. So we have wealth in there, of course, in the theory, but it's going to drop out in the theory. So that's why it's not going to be important. The next thing we do is that we've got a law of disposable house, a law of motion for how wealth changes, and it's just going to follow this standard equation where you have the interest rate in there. In this model, people are going to know the interest rate period by period. So they're going to know what future interest rates are, but they are going to take those into account. Now, if you know what the interest rate is, and often people assume the interest rate is constant, okay, so we're just going one more step there. We're saying, okay, it's not constant, but people know what it is. And then in that setting, we're saying, okay, that actually completes all the markets, because it really allows you to buy any consumption good that you want now, and also just save up for it and buy any consumption good in the future. We could go one step further and say, well, maybe you don't know the interest rate. Maybe you don't know all the things that are going to affect your wealth. And then we'd think about generalizing the model of having just an interest rate in a bank to having markets for contingencies, consumption contingencies, a la de Breu, chapter 7, and then we would have complete markets. Natural benchmark to start from, guys, is that we economists believe that, I believe that trade will take place when there are opportunities for it. And so when we're thinking about deviations, what we'll talk about, when we're thinking about welfare comparisons and what is good or bad, We start from a situation where you get the first best and do the one off and ask, how does this make it worse? If you start from any other assumption, that really means you're saying, well, the combination of these two things makes things as bad as they are. And then the obvious issue is, well, which one do you fix first? That theory of a second best is sort of well developed, but at the same time, we all know, well, I shouldn't say we all know, at the same time, there are a lot of theoretical results that are out there that say, once you back off the notion that people can trade when they want, when you back off that notion, it's really hard to derive conditions under which demand curves slope down, let alone anything else. So that is an argument for thinking about starting out with why you think about allowing people to trade, and then ask what would happen in such an economy. Now, I understand a lot of you guys might disagree with me on that. And in particular, government is in the business of doing things. So if you're telling the government the economy works great, well, how does that help your job prospects? So moving on, something to think about. Here's our set of state variables: wealth, family composition, lagged labor supply, because experience does count in this. It's, if you look at wage regressions and put whether people have taken time out of the market recently, that clearly affects their wages. It shows up all over the place. It doesn't matter which data set you look at. And then we got stuff on whether they got home ownership or not, house size, housing prices, wage rates, a bunch of other things. And so here are our state variables. You can see there are quite a lot of them, okay? So if you wanted to try and solve this model, well, okay, try, especially in estimation. Now, when we get to the counterfactuals, of course, there's enough separability here so that we solve it for each group, or a median group, something like that, okay? So we estimate the model, and this is what we get. I'm not going to go through the estimation right now. I will go through general techniques for estimation as soon as I finish this example, all right? This is what we get in terms of, here's the data, the dotted line, and this is what the model predicts for the home ownership rate. This is for across the ages, okay? And here is the size. Size is not a choice variable, but it is given by both your choice to when you buy or not, and also what kind of person you are in terms of the characteristics. Here's the labor force participation rate. This does not look particularly good, I would say. It's fairly flat in the data, and we get this sort of down, this little bit of a U shape. And then so far as the children are concerned, we're doing okay on this one, over predicting at early ages, under predicting a little bit later on. So we're missing out on those, we're missing out on those births a little bit there. So that's how we get the cross-sectional stuff. And you might say, well, okay, you're using basically a panel, short panel, no surprise that you're going to actually solve for the cross-sectional stuff. What about the time series stuff? Okay, here's the time series stuff. And here's what the model predicts. And here is what happened in the PSID. So we're using 1 period ahead predictions given the state. I should have said that for this slide as well. It's 1 period ahead predictions given where we are now using the model versus what actually happened, okay, in the PSID. That's what's going on. Why do I say that? When you are trying to predict what's going to happen in the economy, if you can predict what's going to happen 1 year from now, and you are on the whole right, you are doing great, because economists, for the most part, cannot come close to doing that. And so thinking about these 1 period prediction aheads is not a bad thing when we're talking about something like time period along those lines. So you can see what's going on in the calendar stuff. Home ownership rate, we're too low. Here's the PSID. Here's the census, by the way. Strangely enough, we're closer to the census than we are to the PSID. PSID is not a balanced sample. And so part of that is being explained by the fact that we're not using a balanced sample. And here we're just lucky. Notice how far the PSID is from the actual census, though. So the unbalance of the PSID gives them a worse prediction than when we apply our model to the PSID and go from there. We're not totally sure as to why we're doing better. We can't say that. If we're looking at kids over this period, this is the, average home size. You can see that it's going up. Again, we're too high. Okay. In that gap, you didn't even want to hear what I really said. So here we are, all right, with predicting not so good on the one period, but the change may be a little bit better, okay? And that's something to think about too, where we're making predictions. And I must say that a lot of this is stuff that is still being developed, not just by us, but by all the people that are lecturing to you. And so this is definitely a field of research where what kind of predictions can we do best at, worst at, thinking about the change as opposed to where we are now might be a better way of thinking about predictions than actually thinking about levels. But anyway, this is what happened in this model. So we asked, well, how can we use this to predict counterfactuals? I've already explained that a little bit, and so spent enough time, I think, on that. Non-stationary, can't predict the time series process, can't really hard to predict future paths. So let's just look at hypothetical stuff. I said, let's look at two steady state economies. First of all, guys, how do we get a steady state economy? Well, in this setup, we've got the demographics of the population changing as well, right? Because as less kids are born, well, obviously population declines. And in fact, in the United States, for the first time ever, the United States population of Caucasians actually did decline. At least that's the latest figures. It's been declining as a share for a while, population growing, but this year it's actually declining. In Europe, you've already seen that. In several countries, you got declining of the whole population. That's fact of life. So and then the question is, where's it going to decline to? Well, it's non-stationary, so maybe it'll calm down. Generate a stationary model. Well, how do you do that? You basically start at 23-year-olds in this, track them through. There are still some guys that are still old, so you wait for them to disappear from the data set, and that means disappearing from the data set doesn't mean dying in this setup. It just means that they're beyond what we'll call the finite dependence period, and that really means beyond their childbearing periods plus 17, okay? Because that's sort of when the last kid leaves. And so that's one way of thinking about, well, how are we going to words? We start with people when in the same position, they take different choices. When can they possibly get back together? Not until the youngest kid has grown up and or left the household. So that's where we get our finite dependence from in this framework. Going back to that renewal discussion and terminal state discussion that we had in the previous lecture, we get a stationary economy that way. And then we just hold the other drivers at their 1971 case and then start moving things around with the preferences that we've already estimated, okay? So what happened? Suppose you double wages, which is basically what they are at 1991 levels. Well, you find first home purchase is postponed, births fall, labor participation increases, okay? So that's a big deal in terms of explaining why did people not buy homes as early as they used to. The simple answer is wages increased. What did that do? Well, labor supply births went down, and they also delayed having births. So the reason for buying your first home, remember, second child, is delayed. And so something not in your market actually is a big driver of what's going on in this setup, okay? Education attainment goes up by 1.5 years, again to 1991 levels. First home purchase is brought slightly forward. See, educated females tend to settle in their job and location earlier than ones that are less educated, a little bit more transient with respect to the workforce. And so as a result of that, they're ready to tie themselves down to a house, or at least pay that first transaction cost earlier on. Now, you might say it has nothing to do with that. It has to do with down payments. And I'm saying, no, 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 complete markets. Remember, I want to go from that. And you're saying, wait a minute, it's really important. Maybe it is, maybe it's not. And so an issue is, what would happen if we had credit constraints? What if we thought about taking that seriously? What if we thought about how that might affect home purchases? Next paper, next research, over to you. After you finish the session. So that's the kind of stuff that is something that you could think about, but education and entertainment, at least in our model, seems to actually bring home purchase forward for that, and we say for that reason. Housing prices increased by 15%. Well, home purchases postponed. No surprise about that, because in this market, higher price for a commodity, downward sloping demand curve. Remember, you don't get it in complete markets necessarily. First home purchase postponed. Labor participation slightly increases because not because of a wealth effect, but because just because other stuff is going on. And this birth barely affected. If interest rates go up, what we see is first home purchases actually brought forward in this model. When you solve it, that's exactly what happens. When you increase the model, when you increase the interest rate, home interest rates brought forward, because, as I said before, you're saving yourself rent down the bottom, down the back end. People are recognizing that. People are understanding that future money buys you more than current money if the interest rate goes up, and that's what's driving it. Now, of course, in a real economy, once you move away from the model and you ask changing things like changing wages, changing, say, housing prices and interest rates, so maybe hitting a supply thing there, well, then these things are going to operate in different directions, right? If everyone brings their housing purchase forward, but the housing prices increase, well, then there's a supply effect. And so that's something else that we're not taking into account. I mentioned before, the supply effect might be kicking in, and then of course the answer is not at all, is quite ambiguous. So that gives you some sense of what you can do when you estimate these models. Okay, I've talked about a specific way of estimating it, but my point is that as economists, when we're thinking about how to model economic phenomena, we make explicit assumptions. They can be questioned, they can be argued about, we can discuss them, unfortunately not so much in this lecture, but overall, that becomes the basis for the dialogue as we think about, well, if you do this, well, then you get that. Now, if you do something that doesn't have the internal consistency, if you go that way, how do we discuss your internal inconsistency? Do we have to start saying, well, you're a very famous person, so you're allowed to make that mathematical mistake? I don't think so. I think that really we should be having internal consistency within models so that we can have a basis for moving forward. Okay. So let's step back from that application, if you don't mind, but it looks like,
sorry?
Go ahead.
Yes,
go ahead, James Martin.
I do have a question. Maybe I missed that, handling two computers here, but is it kind of a crucial assumption in your setup that you are like estimating preferences in the earlier years, and then when you do this exercise, you keep those estimated parameters or like structural preferences fixed when you do this exercise here?
Okay, got the question. Let's be clear. The preferences come back from there, and they are estimated for all age groups. And I am wanting to separate what we'll call household preferences for kids, staying at home, other demographic factors, separate from what we might call compositional effects of what happens when you accumulate more education. So obviously I'm going to have, if we're going to have, for example, in education increase by 1.5 years, what I'm doing is changing the composition of female workers and saying we're going to have a higher proportion of them educated. What happens when we shove that economy through in its steady state? So it's important that, and it's good that we have this discussion now. it's really important to talk about what's invariant, unchanging in the counterfactuals versus what we are changing. And so I'm not changing these thetas at all, or the gammas or the deltas, but I am changing all the stuff that's solved in the model, okay? And so if we go back to the Harold-Zerker case, what I might change is one set of the technology. I might say, well, mileage increases by more than 1 now because the engines are better, but I'm still going to hold the maintenance costs constant. And so that's just to be clear about what I'm doing here is here we ask what happens when the wages still have differences between educated versus not educated. No question about that. But the economy is in steady state. And so for whatever reason, people have, some people get high or low education, and that affects their wages. Experience is affecting their wages. Still endogenous, but we have a different composition of education. That's the sense in which it's a driver outside the model. Okay. And so if we then went back and asked, well, why do people get educated in the first place? Well, maybe it has something to do with what they can buy afterwards. And in that case, if we endogenized education, well, then we'd have to take the model back further. First, they accumulate their education, then they hit the workforce and go from there. I was looking at wages actually, but here's the education one. And then the same with wages. That's something that's affecting things that occur over time. Does that answer the question?
Yeah, thanks. Yeah, I was very interested if you kind of assuming that these kind of structural parameters stay constant over time in this sense, if you think about the time change. So yes, it answered the question. Actually, there was another question just coming up. Maybe it fits quite well right now. So
sure.
There's Diego is asking if like several applications actually rely on assumed values of beta, so the discount factor, rather than estimating it along with other parameters. So he was interested if there are any results characterizing the consequences of assuming an incorrect discount factor.
Sure are.
Bias or factual prediction error.
Let me put this in the most blunt form. Beta can go from 0 to 1. And so if you put beta equal to 0, there goes your dynamics right off. And then the beta is really weighting something about how much you value the future. And so that is something that I would argue probably varies from application to application. It may be true that people have a subjective discount factor that that they hold when they're making all their purchases, make all their decisions. I'm willing to accept that 100%. But the point is, when you're making a specification error, for example, did you put in mortality risk? And if you don't put in mortality risk, that's going to be compounded with your subjective belief stuff. And so obviously you should be putting that in there as well. What about the risk that you get sick or something, and as a result of that, those fancy skis you bought last year are of no use at all? What about that? You don't even have, you might just hurt your leg or something. Do you want to assume the same discount factor for buying skis as if you're buying a house that is more durable, in the sense that you're more likely to live in anyway? Now, if you knew the probability of a ski accident and taking yourself out that way, well, then of course you'd want to put that in directly. But suppose you don't have that. Well, then maybe you want to use a lower subjective discount factor, so beta 0.5 or whatever, depending on how good a skier you are and how much risk you take on the ski slopes. Then if you're buying something else. So that's why I would argue that, of course, assuming an incorrect discount factor is going to screw you up a little bit. And you can actually see that, how much it screws you up, by going back to the Harold-Zerker case that we looked at. And I said there was a correction factor in there. We're going to talk about that in a minute. Correction factor in there, that's all hit by beta. And so you can see, well, how big is that numeric factor and how much is it affected by beta? We'll talk about it, okay? But that's an overall answer. All right, keep modeling. Yeah.
Thanks. I hope, Diego, that answered your question. Thanks.
Okay, let's move on. need to talk about some estimation here. How do we apply CCP in practice? Well, I've already given you an example. But suppose you got either a stationary distribution. So let's start talking about this non-stationary stuff because it's making it harder. Or if it's not stationary, at least let's assume we got a complete history in a steady state economy. So we can see old people, young people, middle people, synthetic cohort of everybody. Okay, so that even though you don't see the same person tracked right through, you see the lookalikes that they will be, after all, they're living in a steady state economy, down the line. Okay, so you can put together what we'll call a synthetic history of people. That's called a long panel, all right? And now, just to go to Diego's question, let's assume that we know beta, and yeah, okay, we don't, but let's go with that for now, because as we know, most people do assume it. And we know the distribution of disturbances, and you might say, ooh, that's also a bad assumption. But let me come back. I'm going to say, I'll say right now, if you don't know this distribution, if you don't know G, well, then your model is under-identified. You've got exact identification if you know G. We'll talk about that in a minute. And so if you don't know G and you want to estimate it, you've got to make some other assumptions about how the systematic factors influence each other. There's nothing wrong with that. You might know that these two things are perfect substitutes, and you might have some variation that allows you to get that substitution parameter. Exactly, okay? But I am saying that there's a trade-off here about what you assume about the unobserved distribution, the distribution of unobservables, versus what you assume about the observables, okay? And let's suppose that you know also a normalized, I'm going to call it still a normalization assumption, that one of the utilities is one. Before I called it J, but then it changed notation. Hope that's okay. We'll just assume that U1 is none. Panel is long, so we can identify the CCP straight off, the correction factor straight off, along the lines that we talked about. So to keep it simple, we got end-independent observations of a whole history. That's just so that I can keep track of my cap ends and T's easily. And then you've got these decisions that they make. You've got a probability distribution over decisions and outcomes. And in this setup with the conditional independence assumption, you've got these probabilities that determine what's going on, okay? So you have, here are our conditional choice probabilities, here are our transitions from one state to the next. So we've got this nice separability here. We've got the P's over here and the F's over here. Providing these things are sufficiently unrelated to each other, well, then you could sort of estimate this separately, and go from there. And that's exactly what people do. Actually, in the Zerker example, of course, we assumed at front, at least for the original, very original sample, that we knew it. It just increased by 1 unit, okay? Not for the Monte Carlo. So these are additively separable. What you could do is estimate these things jointly. So you estimate the F's this way with cell estimators, the P's, the CCP's that way with cell estimators. Dead easy, no parameters involved, okay? And then you say, okay, let's construct this kappa function. This kappa function is found by just starting with action J and then considering going on with the first action. It could have been the cap J, but let's just pick the first action because that's the utility that we've normalized. So this kappa that I'm using here is exactly analogous or almost the same as the kappa that I defined in the first lecture. I know it's a long time ago, at least a lot of words ago. And so really, this is formed by taking, they do this in period T, they do J, and then from then on out, they just take action 1. This is the distribution in tau plus 1 of the X's. And so we can recursively estimate this kappa just by plugging in the estimates here. Okay, you've already got as I said, you've already got the F's and the P's. You're plugging them in here, just moving through it. And so that way we get not just the kappas, but also the correction factors. Again, it's just a matter of going back to the formula for the size. We know they're identified from the P's. We already saw that. And so we got the F's in there, and then we've got this invertibility or representation theorem, and that comes right back to another slide that I showed you in the first lecture, where we said This is actually a Q here, which is just the difference between two correction factors. The Q was identified, and so the difference in these two correction factors is also identified. We talked about that. That's the only reason why this formula differs from the slightly different formula that I showed you in lecture 1. And we have UJT equal to, this is identified, these are identified. So what do? Just substitute our estimates in there right through. And now we have an estimate of our utility function. That's in general. That's not just for Harold Zerker now. I told you showed you how to do it for Harold Zerker. Now I'm saying, if you got a long panel, you got a stationary economy, then you can do it for any of those kind of setups. It's not specific to that example. And in fact, you don't need to use a type 1 extreme value. You need to know what G is, though. Otherwise, you've got to do something else. So stationary case is similar, except you're going to have a sort of a nice matrix representation to go with it. Excuse me. I won't talk about it. Basic point is, law of large numbers means that both F and P are converging almost surely. They have asymptotic distributions. They're just cell estimators. They're independent of each other. And so each of these guys must reach the Cremier-Rao lower bound. And that means that since U is exactly identified, here's the number of parameters you're estimating using maximum likelihood over here. Here are the number of parameters you're using that you want to get at over here. It's a one-to-one mapping between the two, so you can appeal to the invariance principle. In other words, you take a maximum likelihood estimator, you put it through a one-to-one transformation. That means that this thing implies this U hat is also consistent, reaches its Cremier-Rao lower bound. You can't get any more efficient than that unless you put assumptions on the nature of U. In other words, the only way you can get more efficient than doing this estimator is making assumptions about the functional form of U. Nothing wrong with doing that. I want to be clear about this. We make assumptions all over the place. You just saw a few from an article that I'm just about to publish now. So, I can't be one that claims that, just relax all the assumptions. No way. Models consist of assumptions. That's what they are. And then you just work out the implications of those assumptions. So I'm not saying you shouldn't do it, but I am saying that that's what's involved. And that's where you're getting your asymptotic efficiency from when you talk about the difference between maximum likelihood versus CCP estimation. The reason you're getting something more efficient is because of what you're assuming about U. So in practice, when I say in practice, almost every application does make assumptions on U, okay? And so in this case, we're just parameterizing everything as usual. Typically, we assume that not only is beta known, but so is the transition function. We often assume that this is linear, and we often actually, the unobserved variables I already assumed was IID back in this previous slide, but that's something that we usually go ahead with as well, okay? So in this case, log likelihood is then, we can say more about this. It depends on the theta and the conditional valuation functions. And so when we work through that, one thing we could do is just solve for the conditional valuation functions. And the maximum likelihood estimator would come from jointly maximizing, solving for the thetas and then maximizing this guy. Another thing we could do is say, okay, just estimate F separately. Most people do that anyway. Form our transitions from the kappas, as we talked about before, just by using these estimates. Get our correction factors by using the conditional choice probabilities over here with the cells. Then take the V, these Vs, where we just construct these Vs with these correction factors. Okay, get these correction factors, because we've now got the correction factors estimated. Get these conditional value functions. Replace the P's with the P hats by substituting V hat with V in 4. Okay, here it is. So substituting our approximations in there, okay, and then just maximize with 3, okay? So just working through each, and so that is exactly what we did in that in the example that I showed you up front, okay? In other words, we have the U plus a little V hat, and for the little V hat, we put in an approximation. So this is often done, this first step, so I don't really have to talk about that. Here, we're just putting in the F hats over here to get the correction factor. That is simply going to be, in our case, that's just going to be the Euler constant minus the conditional choice probabilities. Since you're always taking differences between 2 of these things, well, this drops out always. Okay, so you're just looking at the difference in log P's. And then you're going for the last 3 steps. We've got that this is equal to U plus this correction factor. The correction factor is coming from before. Okay. And so there's our H hat. That is all this future stuff. See how the betas are coming in here? And so coming to Diego's question, we can easily change the betas around, all right? Plug in different betas on this one, because this one here, these are just conditional choice probabilities. They're coming from the cell estimators. So you can ask quite simply, how sensitive are my estimates to changes in beta? Change it. All you do is change the beta at that point where we're putting this together. This is numeric. This is numeric. Add it up with different set of betas. That's why I said if beta is equal to 0, it's simple because this becomes 0 and this wipes out altogether. But if more generally, put any old beta in there. Now you've got a logit in which you have static model with a correction factor in here. These are numbers, guys. This is a number that comes from the estimates that you did at the what we'll call pre-estimation stage of the P's and the F's. And so that then becomes the QML. It's kind of has a lookalike formula for a static model, has a logit kind of look about it, and then you go from there. Okay? So that is why I'm arguing, you know, first round estimates, it really means just doing this and getting that. It's your choice. You don't have to do that. You could do something else. You could take a minimum distance estimator, and that's going to actually be easier, even easier than what I've described. Form this vector function. Here's the difference in correction factors, and that is found by essentially the difference in the valuation function, conditional value functions. And here I'm just subtracting from this kappa, these distributions that are formed from what happens if you follow path 1 from the very beginning versus what happens if you follow J first and then path 1. Okay, look at that. Okay, ooh, 9:57. Oh, 10:30, right? Or when do I have to stop? 10:30, right? Yeah, good. For a minute, I was worried. So here we've got, again, we're going to estimate these 2 things. Those are the difference in the log P's. This one's a little more complicated because we've got to add up those differences in log P's and combine them with the kappas that we recursively get. Recall, the kappas are just coming from here. A little bit messy here, but it's good enough, I guess. Maybe, no, that's not. Kappa's coming from here, where we've estimated tau plus 1. That's how we get the kappa tau. So we get that estimate, okay? Now minimize the quadratic form. Here's our because the argument is going to be that this thing here is actually the utility in its unrestricted form. Why is that? Look at this. Go back a few slides. This is why I'm suggesting that it's useful to look at your own slides. See that? There's the unrestricted utility. No restrictions on it. Okay? Now we put restrictions on it. So we estimate the unrestricted utility. Here it is. And then we ask, what's the difference between the restricted utility versus the unrestricted utility? Well, how do we do that? Put in a quadratic. First of all, are the restrictions satisfied? Okay. So you can get that straight off. It's a straightforward test, chi-squared test, right? Because you've only got a given number of x's, given number of p's, and so you can do it from there. And the second thing is, regardless of whether it's accepted or whether you accept the null or not, you can just take the minimum here, get the theta at the minimum, and estimate it that way. But there's actually more to this. Firstly, by taking a minimum distance estimator this way, first of all, you get the unrestricted. Then you get a test. I've just explained. You get a test because you got a quadratic. Then you can also impose it. So you've now got a estimate of the theta. What about this argmin problem? How easy is that? Well, let's suppose that this is linear in theta, as it is in almost every problem that you will look at, because you're going to take, no, I won't say that, in a lot of problems that you look at, because you're going to take that beta is a given number, and then you're going to have this systematic part of utility is going to be linear. Well, what does that mean? You got linear stuff here and number here. That's what I call least squares. And so you have a closed form solution to this whenever this is linear. Okay, so that's how fast it is if you're using this minimum distance estimator. And not only that, suppose there are a lot of paths that you could take, and you're thinking, oh, I don't want to compute all these paths. What a pain. Why don't you just simulate them? Simulate the paths out here, and then just bang the functional form assumption here. This minus this is a simulated path that's linear again, because the simulations are linear. We're not talking about simulated maximum likelihood here. We're talking about simulated methods of moments. Okay, so the asymptotic distribution is well derived, and then you just go from there and get an estimator out get an estimator out that way. Now, having give all the pluses, spent like, I don't know, tons of minutes on CCP, I'll now spend 5 seconds on its minuses. And the minus is that you get an estimator which is less efficient than maximum likelihood. No way of getting around that. And so how much does that efficiency count? It's going to vary from application. You got a small number of observations. You got to make a lot of assumptions about the model in order to get anywhere. Well, then you're probably thinking more in terms of maximum likelihood. You go for a big data set where even you have to where even though there might be a lot of different categories, that's not the issue, guys. It's not how many observations in each cell, because after all, you are averaging over cells to some extent in order to get to the numbers that you really care about. The numbers that you really care about are actually aggregates. They're things like, how much will this change overall? And if you're thinking about, well, how much will this change for the top 1%? Do you really think that by doing maximum likelihood, which is going to be based on most of the observations in the data, that your data is going to really give you an accurate kind of prediction on these outliers? Just think of a linear model. Think of where your data is, and then you're trying to predict an outlier. I don't care what method you use. You've still got that problem. And so the cell problem, I said cell problem, and it doesn't go away when you do maximum likelihood. If you're trying to predict what's happening out there where you've got hardly few observations, because the estimator that you used is going to be driven by where the bulk of the variation is happening. And if it really is, if in fact the maximum likelihood is driven by those few observations out in the extremes, well, then it's probably not a very good predictor of the middle. So I want you to be clear about this, that not having enough variation in different spots is something that can potentially affect different parts of the estimation. And you can't just dismiss it by saying, oh, there aren't very many observations in this cell. Have to think a little bit more deeply about that kind of issue. What is it you're trying to predict? Where are you going to be, what is your estimation going to be based on in terms of the variation? And then how do you work it out from there? Having said all that, I'm still arguing that if you've got, and then I wanted to say something else, that we're using these conditional choice probabilities for different parts of the population as a way of doing sort of a two-step aggregation. That's really evident from the minimum distance estimation, because here in a minimum distance estimator, what you're really doing is saying, I'm going to aggregate the data in this way. That's how I'm going to aggregate the data, by getting an unrestricted estimator of what I want. And then once you've got an unrestricted estimator of what I want, then you think about, well, what kind of restrictions do I want to impose? Why do I want to impose those restrictions? Because maybe I'm interested in the theta. Okay, you might be interested in something else, not the theta. You might be interested in some elasticity, and then maybe you want to do a transformation of this thing to the thing that you're interested in. Again, that's taking us a little bit far down the court, down a two lectures component, but series. But my basic point is here that ultimately you're concerned about the end product. You guys do dynamic programming, in heaven's name. You should be able to see that. And so what you're concerned about is how these different pieces affect the end thing that you're most interested in. And so that's the sense in which, yes, we're doing the aggregation in a non-efficient way here, because we're not imposing all the restrictions that maximum likelihood gives you, but the restrictions that maximum likelihood gives you are coming from the assumptions, directly from the assumptions that you put on the systematic part of the utility. They may well be justified. And if you can justify them outside the data set, of course you should impose them, because they are restrictions that you can use as information. But if they're not coming from the outside of the data set, and if it's just a matter of convenience, then the arguments, I think, are not so clear.
Perfect. Yes. Okay. And then let me ask the question
of course
of Kim. So the question is regarding the QMLE. There's no common statistical inference. So is it correct as a last step that the asymptotic variance of the estimator should be adjusted for valid statistical inference?
Absolutely. And so it's a two-step estimator. And so need to adjust the fact that you're doing a two-state estimator. Okay. Now, standard formula on that, Whitney Newey, 1984. And actually, there's more recent stuff, essentially on the working papers now. We, instead of adjusting in a two-step estimator, you actually adjust the orthogonality condition directly. And so there are ways of doing the adjustment, a couple of ways there. And if you adjust the orthogonality conditions directly, well, then there's no loss in asymptotic efficiency. It's more computationally, there's a loss in asymptotic efficiency, regardless of which way you do it, by virtue of the fact that you don't impose the functional form that's implied by the P as a function of X. In other words, solving the valuation function. That loss in a CCP estimator is there, all right? And the only way to get rid of that loss is to compute the policy function once and then do a one-step correction. And there you go to Aguirre, Geberia, and Mirror to do the correction, okay? If you don't do that, well, then there are there's one loss that I just talked about. The fact that you're not imposing the functional form of the P, which comes numerically from solving the Bailey function. The other loss, which I think Kim was referring to, is the fact that you're actually estimating the conditional choice probabilities as frequencies. And that means that you have to do an upfront correction to get the asymptotic distribution of the thetas. Now, in the Monte Carlos that I'm showing you, all of that is done. Okay, it is done. So that's the sense in which I'm not cheating by pretending to put in the P's. No, actually, well, sorry, for the Monte Carlos, we're just doing simulations. So what am I talking about? But in applications, that's what you should do. It was done in, let's see, the stuff with Natalia. You, instead of doing a two-step, you could, and this is pretty much on the research frontier, you can think about doing the correction using directly the stuff that's been done by Chernozhukov and Nui on adjusting on adjusting the moment directly. I won't talk about that more, but those are two directions. One of them is standard, two-step correction. The other one is not at all standard, but it's coming. Good. There was another question out there. I see. Was that Kim's? Oh yeah, that's a yes. I can hear. Right. So let's move on. I want to talk about unobserved heterogeneity, at least briefly. What if you relax the assumption that the epsilon's a type 1 extreme? We can do that in several ways. One is to just assume that it comes from a different distribution, for example, nested logit, and then you've got an extra parameter to estimate. You could just go from there. And then you'd have a dynamic correction factor that would be different, would involve a parameter, and you just solve exactly the same way as we do now. So that wouldn't require anything special. But suppose they entered the state variable as well. Okay. Suppose it entered the state variable as well. So you've got these different brands. I mean, I think we call them Fords and GMs, and that's totally apocryphal because Harold Zoka only used GMs. So different brands for this audience, especially since John and Bertel are in there. Different years, maybe, different types of bus, different type of GM buses. And we don't see what the brands are because unfortunately that data was never collected. And there's a different cost depending on whether it's one brand or another. How would you estimate that model? Well, the way to go about that is to think about the following setup. First of all, just imagine, just for a minute, that you knew what the conditional choice probabilities were. Okay, that is the values of the conditional choice probabilities. For each X and S, you knew what P was. You don't really have to know what the function is, but you just know what the values are for each of the X's. And suppose you know that there's an unobserved state S. You don't know what the probability distribution of that is. Different brands of different buses, two types. Okay, and then what you might do, a maximum likelihood for this easier problem when you actually know what the value of the P's are, is just to go ahead like this. You've got the probability of being these different types. You got the log. This is the log likelihood. You got to worry about the likelihood of this times the probability of it being this. Notice you got this stuff inside the log, pain, in terms of the estimation. So that would be one way of doing it. Conditional value functions are taking this form here in this setup, and so we could potentially do that, but that's what's involved. Okay, this is how the EM algorithm works essentially. You imagine that you're going to pick theta somewhere and pi somewhere else, and you ask, what is the probability that this bus is a type S, given these are the mileages and replacements that I've seen from this bus? What can I learn from this bus for the whole history that I've got? And I also have all these X's, these are the mileages, and I know what the parameters are too. And I also know the unconditional probability of it being a type 1 bus or a type 2 bus. I'm going to call it forward a GM, excuse me. So what's the probability of this particular bus in my data set being a Ford or a GM? That's what this Q is. And you can see where it comes from, because just take this set of formulas. You can see that if you multiply this by this, you will get that. That is the joint distribution. Okay, so it's just breaking up the conditioning in different ways, sometimes called Bayes' rule, but not really, just different conditioning arguments. Now, you also, if that was the case, well, then that would give you a probability that this is a particular type of bus, but it'll also tell you, on average, the law of large numbers, I mean, what the probability of it being a Ford bus unconditionally, because all you do is average across all the different buses and go from there. Okay, now that sets up an iteration, really, because then you might go, well, suppose I know, or I'm willing to make a bet on this guy. What is my likelihood? Let's just maximize that. It's not quite likelihood. Let's just maximize this. And what is this really saying? Look at this. Suppose this is a 1 or a 0. In other words, suppose you knew the type of the bus exactly. Then this would just be a maximum likelihood estimator. If we knew what Q, if Q was 1 or 0, okay, and it didn't change. But it's not. It might be a half, or it might be 3/4. So basically what we're doing is a kind of weighted average of each of the likelihood pieces, where we're ascribing each bus to being, well, we're not quite sure what it is. It could be a Ford with 3/4 or a GM with a 1/4. So let's just weight down what was likelihood by a 3/4 versus a 1/4. Okay. And then we go ahead and maximize that. Okay. Now, if you do that, you get the same set of, first, in a standard EM algorithm kind of setup, where you start out somewhere and you keep going, you're imputing things. You end up with the same set of first order conditions that you would if you did maximum likelihood. So it's telling you a local maximum, not a global. Just want to be clear about that. But nevertheless, it's a very useful tool that you guys will probably use. So how do we go about it? Compute this guy by using the previous estimates of our PM and theta M. Okay. Then compute this one by just taking the average of the Qs. Update our Ps using one of two rules that I'm going to give you in a minute. And then once you've got the Ps, updated Ps, just go ahead and maximize according to this weighted, not really likelihood, but weighting each piece of a likelihood that way and going from there. Okay. Pretty straightforward. What are the two ways you could do it? One is you could just, well, you already have the likelihood right here. So why not just plug that in? That is one way of doing it. Notice that that is not really the likelihood in the sense that maximum likelihood, because really it's a likelihood based on almost a fake likelihood in which you're plugging in conditional choice probability values. In the same way we plug those choice probabilities in the Harold-Zerker case where there was no unobserved heterogeneity. Remember, we had a correction factor. It was the utility, current utility, plus this log odds thing that was added for the correction factor. We had P's in there. That's what I mean by log, this sort of quasi-log likelihood. It's not quite the likelihood associated with this. This way is pretty straightforward though, too, because this is just an average. We're just taking averages. And the question of which one you want to use. Now, there are some asymptotic properties associated with this. There's a very recent working paper by Adam Deering, D-E-A-R-I-N-G, now at Cornell, formerly at Ohio State, that discuss the asymptotic properties of this estimator, don't have a discussion of this paper, of this, they yield pretty similar results, though, at least in Monte Carlos. What do we get? Well, here is what happens when you ignore unobserved heterogeneity. If you ignore unobserved heterogeneity and you think it's playing a role, in other words, there's a good reason for putting it in, then you should do it. Because if unobserved heterogeneity is important and you ignore it, well, what tends to happen is that although it's really fast to compute, the mileage stuff tends to play a smaller role than it should. It sort of comes back down. And the intercept stuff plays a bigger role than it should. It's like ignoring, well, it really is ignoring an regressor. Think of what goes on. You're kind of slurring over something that really counts. So as a result of that, the constant is rebalanced and the effect of the other stuff is diluted because it's not taking account of covariation between the two regressors that you might use in a linear model. Well, in a non-linear model, it's a little bit more complicated than that, because even if the regressors aren't correlated with each other, through the non-linearity, it still will have an effect. But that's kind of what, but the similar kind of intuition applies here. So you don't want to ignore unobserved heterogeneity when you think it's important. Now, what you don't want to do is fall into the trap of saying, well, there's unobserved heterogeneity all over the world, and so my model doesn't capture it. Because if you fall into that trap, you're basically saying, well, what use is the data? Because if there's enough unobserved heterogeneity in the world, well, the data won't produce anything for you. And what we're in the interest here, what we're interested in here is not the truth. Leave that for the politicians. What we're interested in here is moving forwards, explaining a little bit better so that we can get better counterfactuals. And so my argument for what I would argue with respect to unobserved heterogeneity, if you think there's a good reason for it, yes, put it in. But if there isn't, well, probably you should be thinking about leaving it out. Well, anyway, you put it in, you do full information maximum likelihood, doubles the amount of time if you're doing full information maximum likelihood. This one goes up by a lot more. Okay, and you might think, whoa, does this actually catch up? Actually, not at all. Really, what's going on? This one only computes, you've already incorporated it. This one is computing CCP estimators again and again and again, right? In that step 4 or one of those steps, you go back. It has to do that maximization problem several times, about 50 times in these applications before you get convergence, and so that's what's taking the extra time. In larger problems, this one gets blown out of the water, of course, and that's why I didn't bother giving you a maximum likelihood estimator of the game stuff. When you start putting in time effects, well, again, it's increasing even more. It's doubling, going to 11 minutes, but still computationally tractable. So that's not really something that should bother you too much. So that's really all I've got to say. The only thing I would, I'm going to take, I'll get to the discussions just a minute, and then we can talk. The rest of the time we'll just have discussion questions. Just look at the last slide if you're possibly interested in the Helsinki. Cyprian, who's actually sitting right there somewhere. Where's your hand, Cyprian? Come on. Oh, there he is, right at the back. They turned around, but he'd already put it down, but he's sitting right at the back. He's actually there, but there's a website. Save him sending tons of emails. Just hit that website and go from there, or talk to him, whatever. Okay, let's go back to the lecture in hand. Questions, comments, go for it, guys.
Yes, Bob, there was one question by Yayi Wen about identification of different types. So could you share some intuition about the identification of types when was talking about unobserved heterogeneity? So what variation helps to identify the probability of being each unobserved type?
Good. Notice that we said that when there's no unobserved heterogeneity, It's exactly identified if you know the distribution. So the only way you can identify a model when there's unobserved heterogeneity is by putting restrictions on the way the observed variables are affecting the ultimate solution. So here we've got a ton of restrictions, because basically what we're doing is saying that regardless of where we are in miles, the only way miles are affecting things is through this linear term, or we could put a quadratic in there. There isn't a separate coefficient for each number of miles. So we have a utility which is linear in, oh, here we go, linear in X. What if it was quadratic? What if it depended on everything? What if it depended on the actual number of miles? So in other words, we're reducing the number of the parameter space that way. And then what we're asking is, we're hoping that those restrictions are enough so that when we take the log likelihood, and instead of, for example, taking the score, instead of taking the score of the log likelihood, we took the score, we took the expectation of the score, and then asked, does that have a unique solution? That would then give you an answer to whether there is, whether you're identified or not. Because you're in a maximum likelihood situation, remember it's based on the score, and you're asking, does that score uniquely converge to a unique fixed point, or are there lots of them? So of course, when you're looking at log likelihood, it's a highly nonlinear equation, and it's kind of like, I don't know, just kind of hoping. But most of us do that. Actually, when we do GMM nonlinear stuff, we say, well, assume there is a unique solution to this, or assume that it's almost unique in the sense there's a little OP1 that might change things. But really, what in a simple linear model, we're asking the question, is the rank condition satisfied? Really easy to work out in the linear model, because now we're just asking whether one of the equations is a linear combination of the others. In a nonlinear setup, well, maybe not. People tend to think that nonlinearity is going to help you, and yeah, I tend to agree, but that's not a theorem. And so whether you get identification or not is going to depend very much on the particular application that you look at. So the couple of papers that may be worth looking at this are worth looking. Kasahara and Shimotsu in the early 2000s have a simple setup in which there is, I think, restrictions on the payoffs that allows them to get that. And then they talk about rank conditions that have to be satisfied. And then Ho and Schum have another Journal of Econometrics paper, much harder to really translate to practical applications, but does discuss, analyze how you get identification when you've got this unobserved heterogeneity. I think that this identification question is really important, because even if you, I know I'm out of time, even when you have something that's only set identified versus point identified, and almost all econometrics is, or applied econometrics on point identified problems. But even if you've only got set identified stuff, you can still do the counterfactuals. It's just that the counterfactuals will also be set identified. And so you trace out the parameters that you get in the set identified stuff, and then you see what that implies for the counterfactuals. And moving across now, some of the stuff that I've done with Gale, Restart 2015, does that for principal agent problems. But I think that's an area we should be thinking about moving in. Long answer.
Thanks a lot, Bob. Are there any other questions here from people in the audience? on site? Or other questions online? Because okay. Otherwise, let's thank Bob also for this second lecture. Thanks so much for being with us. It was really great. Although it would have been fantastic to have you on site, but I think
I'm sorry.
next year again. But it was really great that you kind of gave those two lectures. And I mean, as a long-standing lecturer of the DSE, it was really fantastic to have you.
Thank you.
So let's give him a big applause.
Thanks very much, guys. Thank you. And all the best for the rest of the week. Work hard. Become